Now let's move on to study the important properties of parabola. So the first one is the circle drawn by taking the segment joining any point on the parabola and the focus as diameter touches the tangent at vertex. So let's consider what does this mean. Suppose we have a parabola and this is the axis. Let's consider this as the focus. Okay, and this is some point on the parabola. Okay, now if we join these 2 points, that is the focus and some point on the parabola, and if we draw a circle by considering this segment as the diameter, then okay, I'm just drawing it approximately. Now this circle will touch the tangent at vertex. Now the vertex of the parabola is this particular point. That means if you draw the tangent, it will be nothing but a vertical line like this. Okay. And it will be touching the circle that we just have drawn. Okay, so that is what this property says. Okay, so if S is the focus and P is any point, then the segment joining these 2 points, if it's considered as a diameter and a circle is drawn, then it will touch the tangent at the vertex of the parabola. Let's go to the second property. The circle drawn by taking any focal chord of a parabola as a diameter touches the directrix of the parabola. Right. So now here let's consider a parabola with its axis and the directrix, which will be at a certain distance. And let us consider symmetrically located focus. Now by focal chord we mean any segment that passes through the focus of the parabola and it meets the parabola at 2 points. So if we denote those 2 points as A and B, so this segment AB is called as the focal chord. Now if we draw a circle considering this segment AB as a diameter, then it will touch the directrix as shown here. Okay, that is what this particular property says. So here that circle is going to touch the directrix of the parabola. Now related with this, there are a few more properties as we'll see immediately. Tangents drawn at the end points of a focal chord of a parabola meet on the directrix. So here if we have a parabola, and this is a focal chord. Now if we draw the tangents at the end points of this particular focal chord, we will observe that the point of intersection of these 2 tangents lies on the directrix of the parabola. So this is what this particular property is saying. Since it's a focal chord, clearly it passes through the focus. That is what is the meaning of focal chord. And related with this, there is another property. If you observe, we have just seen that if we draw a circle considering the focal chord AB as a diameter, then it touches the directrix. So clearly, since AB is the diameter, we must have the angle between the 2 tangents to be a right angle. Now connected with this, there is another property, that is for this particular point A, the parameter is T1 and the other extremity, that is point B, if we consider the parameter to be T2, we are seeing that the tangents drawn at these 2 points are at right angles. We know that the slope of the tangent drawn at a point whose parameter is T1 will be nothing but minus 1 upon T1, and slope of the tangent drawn at point whose parameter is T2 will be minus 1 upon T2. And since the 2 tangents are at right angles, clearly their product, that is minus 1 upon T1 into minus 1 upon T2, will be equal to minus 1. And hence clearly we have T1 into T2 also equal to minus 1. So this is what is given in the next property. That is, if T1 and T2 are the parameters of endpoints of a focal chord of a parabola, then T1 into T2 is equal to -1. This is very much similar to the result of two perpendicular lines. We know that the slope of the two lines, if they are M1 and M2, which are perpendicular to each other, then the product of the slopes will be equal to -1. So we can remember that on the similar lines. Right. Let's go to the next property. It says the foot of the perpendicular drawn from the focus to any tangent of a parabola lies on the tangent at vertex. So once again, let's consider a parabola with its axis and the tangent at vertex, which is a vertical line, and here is the focus somewhere, so S. Now what this property is saying is, suppose we consider some general point, say P, on the parabola, and if we draw a tangent to the parabola at that point, and to this tangent if we drop the perpendicular from the focus, then that foot of perpendicular basically will lie at the same point where the tangent is cutting the tangent at the vertex. Okay. So the foot of perpendicular drawn from the focus to any tangent of a parabola lies on the tangent at vertex. Let's go to the next property. The length of semi-latus rectum is the harmonic mean of the two parts created by the focus on any focal chord. If we recollect what is the latus rectum, then we know that if S is the focus, then if we draw a perpendicular segment to the axis of the parabola and let it meet the parabola at 2 points L and L dash, then L dash is called as the latus rectum. Right. Now if we consider any focal chord in general, so let me denote some focal chord here, something like this. Let us call that as chord AB. Right. Clearly, since the focus is going to divide the focal chord into two parts, that is AS and BS, right. And we have LS as the semi-latus rectum, because semi means half. Right. So what this property is saying is, the length of semi-latus rectum, that is LS, is the harmonic mean of the two parts created by the focus on any focal chord. So therefore the length LS is the harmonic mean of parts AS and BS. Okay, so the lengths AS and BS have their harmonic mean to be equal to nothing but LS, of course, which is equal to L dash S also, because both are having same length. So since we know the formula for harmonic mean, we can also write that as a formula, that is length LS is equal to 2 times AS into BS upon AS plus BS. Right. Let's move on to the next property. Length of tangent between the point of contact and the point where it intersects the directrix subtends right angle at the focus. So let's read once again. Length of tangent between the point of contact and the point where it intersects, the it means the tangent. Okay, the point where the tangent intersects the directrix, that subtends a right angle at the focus. So let's consider a parabola with directrix and the focus. Now let us consider some general tangent drawn to the parabola at some point. So this is a general point P, this is the focus S, and let us consider M as the point where the tangent intersects the directrix. So what this property says is, this particular part of the tangent, that is segment PM, it subtends a right angle at the focus. So if we join M and P to the focus, then they subtend a right angle. So the angle PSM is a right angle. Moving ahead to the last property, that is a very important and interesting property, that is a reflective property of parabola. It says that a ray of light parallel to the axis of parabola, after getting reflected from the parabola, passes through the focus. And this is true for the reverse situation also. So what does this mean is, let us imagine that we have a parabola, okay, and this is the axis of the parabola. Suppose that there is some ray which is coming parallel to the axis. So we can imagine any parallel ray like this. Now when they all get reflected from the parabola, as if the parabola were a reflective mirror, okay, then on reflection all of them will pass through the focus. So that is the reflective property of the parabola. So this point is precisely the focus S. And it says that this is true for the reverse situation also. That means instead of light coming parallel to the axis and converging in focus, suppose we keep the source of light at the focus itself. Okay, suppose we keep a bulb at the focus. This is S. Then the light will obviously emanate in all the possible directions from the focus. Okay. But when it gets reflected, it will travel parallel to the axis. So all these rays which initiate in all the possible directions, but on the reflection they will travel parallel to the axis of the parabola. So that's the reflective property, and this is used in the parabolic mirrors or solar cookers.